Let me start with the second session of this lecture. In previous lecture slide, we found out that eventually the gain increase or phase delay, additional phase delay will destabilize the system, make stable system unstable. So it is better to define some margin, okay? But there are two types of margin, two kinds of margin, gain margin and phase margin, because there are two sources of being unstable, so we should separate them, okay? When we are thinking one thing, the other thing is fixed. Otherwise, we'll mix up, okay? So I'm using this kind of analogy many times. There is a bank here, and this is the water level, reservoir something, okay? And this is the speed of this flow, this flow of water, okay? There are two ways of this overflow of water. One is if the increase in water level, so then this will go like this, the dam will collapse, okay? Then how much water level can be increased is maybe this is the one of the margin, gain margin. For example, gain margin. And if this is the speed of the stream, okay, this is okay. If the stream is increased this much, this speed of flow is increased this much, then this flow will make some click here, and water will come out this initially, and this dam, this bank will collapse, okay? So difference in this, the speed of the water flow is another margin. Maybe this can be phase margin, okay? So margin, the meaning of the margin is important, okay? So margin is, okay, so suppose you have the engineering pad, engineering note, okay? You can use the scratch something. Then engineering pad looks like this, and there is a grid on it. So you want to write down your equations within this grid, okay? But this is possible. You can go out. This you cannot go out. You can write down something, and also you can go this much, okay? So this direction is, for example, GM, and this direction is PM, okay? There are two different margin, okay? If you go out margin, there's no paper at all, okay? Within this, you can write down something on here without grid, okay? So this kind of things, right? Because there are two sources of making system unstable. One is gain. So suppose this is originally stable system, okay? Suppose phase is fixed and the gain is increased twice, okay? So gain is increased twice, then we will pass this critical point and the system becomes marginally stable. So this is called gain margin. How much we have gain, okay, before becoming unstable. So when you are thinking about gain margin, just take a look at the frequency where the phase becomes minus 180, okay? Gain margin is determined at the frequency where phase becomes minus 180 degree, okay? There is no frequency. Then gain margin is infinity, okay? Whatever gain increase you introduce, system remains stable. That is the meaning of this, okay? So gain margin is amount of gain increase that can be added to the loop gain magnitude while maintaining the stability of the system. And for this evaluation, we assume the phase remains constant, okay? Phase remains the same, then phase characteristics remain the same, then we define gain margin, all right? So this is a gain margin of 2, okay? Gain increased by twice, then this point will move this, okay? So you are evaluating gain margin at this frequency where the loop gain magnitude, loop gain phase falls this minus 180 degree, okay? So this is the representation of gain margin in Bode plot. No, in polar plot. And the same information will be transferred to this plot. Okay? So this black line is original stable one. So at this frequency, where this phase collapse to this frequency, this value, gain is below this 0 dB line. Okay? It's smaller than 1. How much smaller than? This much. Okay? So this should be 6 dB. 20 log 2 is 6 dB. So this value is minus 6 dB, and the gain margin is 6 dB. So this is GM. GM gain margin is 6 dB. Okay. So there is a meaning of this. Magnitude increase of the loop gain is stretch out the loop gain polar plot, or enhancement of this one by this much, while maintaining this phase characteristics unchanged. So gain margin is this one. Gain margin is 2. Okay. If you double the feedback gain, system becomes marginally stable. So this is about 6 dB. So it has 6 dB margin. This is small margin. Okay. Usually you need larger than this, 12 margin or 10 dB. 12 dB sometimes. But this might be okay, but this is rather dangerous for some case. The same concept can be applied to the phase margin. The phase margin is this one. So suppose you have this. This is stable. But if you add some additional phase delay, this polar plot will rotate in clockwise direction without changing its radius or shape. So if you rotate this 45 degree, this one. So you have a margin of 45 degree. That is the phase margin. So when you are evaluating the phase margin, you should take a look at the frequency where the magnitude becomes 1. Okay? So this phase margin is determined where the same thing. Okay, I don't need this. Okay, Tm, magnitude of the loop gain, becomes 0 dB. Okay, so you should take a look at this. This unit circle. Unit circle is passing. Unit circle is the same as crossing 0 dB line in Bode plot. Okay, so while you are doing this, the magnitude is fixed. Feedback gain is fixed. Okay, the phase margin is amount of phase delay that can be added to the loop gain phase before system becomes unstable, and this one is important while the gain characteristics remain the same. Okay, what will happen if you change gain and phase altogether? Maybe we don't know. Okay, it depends on the way of changing it. So this is not important. So one thing should be fixed to define something. Okay, phase delay in loop gain is same as clockwise rotation. Clockwise rotation of loop gain polar plot. So for this particular case, PM is this angle is a difference between this and this. Okay, this is minus 180 degree, and this is minus 135 degree. So you just take the magnitude. Okay, so minus, forget about minus, and forget about minus, and difference between them is 45 degree. So you have 45 degree of phase margin. Okay, so when evaluating this, you should watch this unit circle crossing point, and in Bode plot, you should take a look at this point, 0 dB crossover point, and at that frequency, if phase is less than this, that is more negative than this, that means it is going like this. Okay, unit circle, it passes like this, is already unstable. Okay, so this, when phase is, this is current phase is delayed 45 further, then that means this is clockwise rotation of 45 degree, the system becomes marginally stable. This is called the phase margin. Okay, so gain margin and the phase margin, two different concepts. So you should know at what frequency the gain margin becomes apparent, and what frequency the phase margin becomes apparent. Okay, when you are interested in phase margin, take a look at this 0 dB crossover frequency. When you are interested in gain margin, take a look at the frequency where phase becomes minus 180 degree. Okay. If there is no phase, no such a phase, then any gain increase is okay. Okay. All right. Suppose this one stays, no phase stays, no. There is no 0 dB crossover, then TM is always here, then there is no phase margin. You can add any phase delay without making system unstable. Okay? There is the definition of this. So think about this in solving one problem of your midterm test. Okay? But you should think twice or very carefully. Okay. Let me take this example. This is the first example I introduced to you when I start talking about this topic. So previously, this is the buck converter, and this was stable, originally stable. So this compensation component was selected to make a system stable, and I intentionally changed these values to make a system unstable. So this is a response of stable system. At this point, this parameter have been changed to make converter unstable. This start this unstable oscillation. All right. So how about the loop gain characteristic of this? So this is the loop gain characteristics corresponding to this state, stable state and unstable state. Okay. So in two different environments, loop gain is evaluated, and this loop gain can be calculated using small signal model or measured experimental using some experiment with impedance analyzer, and or simulate with PSIM using computational method. Okay. So this is the original one. This is stable one. So stable one is this. So take a look at this. At this frequency, this is 0 dB frequency, and phase here. So difference between phase at this frequency and this minus 180 degree is what? Phase delay. So this has large phase margin of this much. I don't know this value, but this phase margin is more than enough. Okay. So how about gain margin? I don't know this part. Okay. But still, if gain increase so much, but still phase is somewhere, this is very difficult to define the gain margin. Okay, so you don't have to worry about this. But eventually, if you increase this phase, so gain will go to this direction. It becomes apparently smaller than this. Then maybe you start worrying about the gain margin. But forget about gain margin here. Huh? So phase margin. So stable design was this. This becomes unstable, and this unstable design, the gain, feedback gain is decreased somehow, but this phase becomes very bad. Okay, phase is about the same as this one, so it becomes marginally stable system or unstable system. So there's just some, I don't know. Okay, so this is bad design. So this is a design I made. Maybe this is the phase is slightly smaller than minus, more negative than this one. Then we have the growing oscillation. Okay, making the sustained oscillation is not easy. Okay, I have shown that. I spent some time to get that result. So to have this critical value is not easy. You need tune the numerical value of everything. Okay, so here we have phase margin of this much, very stable, but with this new compensation parameters, the system becomes unstable, and it starts showing this growing oscillation. How about the polar plot? This is a stable polar plot. So this crossing over frequency is unit gain, unit circle crossing over frequency is this, and the angle difference is phase margin. This angle and this angle should be same. Okay, so this is the sufficiently stable, but with some new design, this loop gain is changed this one, and this one encircles this point, or this crosses, this is the region A, this is point B, region C. It goes crosses region C, so it is slightly unstable. So it shows growing oscillation. Okay, so you are using this. This is nothing new. This is the typical example of classical control theory. The purpose of our modeling and the purpose of studying this is we want to use our previous knowledge about linear time invariant system directly applied to this nonlinear time varying PWM converters. Okay, without the background we went through is impossible. Okay, there is no theoretical background to do that. Okay, so now we walk through something. Okay, we skip the small signal modeling, and we'll cover that later. With that part of study, everything will be complete. Okay, then this one is okay. So we are the conclusion is you are using this conventional approach to determine stability margins of this converter using the old story. Okay, this is very nice. Okay, so of course there is some limitation. Okay, this is a nonlinear system, but buck converter is almost a linear system. Okay, if you take a look at the circuit structure, the only difference between on time and off time circuit is just the presence of input voltage. One is input voltage Vs, the other one is input voltage of 0. Okay, circuit structure remains the same, so buck converter is very similar to the linear system. So for the buck converters, this kind of analysis is widely applicable to large step change, large input change, and whatever situation. But the case of other converters, for example, boost converter, the structure of on-time circuit and off-time circuit is different. Circuit itself is different. Okay, is in the buck converter, only presence of the input voltage was the difference. But for the buck and other converters, the circuit structure itself is different. Okay, so there is just some limitation applying this theory to the buck converter and the buck boost converter. No. Boost converter and the buck boost converter, but buck converter is okay with this type of analysis. It's very good, very accurate for the wide range of operational changes. Okay. All right. Let me finish this. Okay. So this example of PCM simulation. This is the AC injection, and this is the parameter for this 65 degree of phase margin. This difference is 65, and I modified these 6 parameters, and with that the phase margin is decreased this much, and I further modified this, then phase margin is running out. Okay, so this converter is almost unstable. Okay, so nothing is changing except the value of this. Okay, we know clearly why we select this structure, how to determine this value to have desired phase margin or desired closed loop performance. That is the purpose of this class. Okay, one purpose of this class. There are many interesting stories. So now maybe you feel comfortable when you are applying the knowledge about linear time invariant system to this PWM converters. That is the very basic thing about this study. Okay, we stop here. All right. So see you next week. Okay, and Monday is the deadline for the solution posting. Okay, thank you. Have a good night.